So as I mentioned, we need to write a VUMAT in Abaqus. The VUMAT is, what is it? It is a subroutine which enables you to define any constitutive model in solid mechanics. So it's a very flexible module, and if you learn it, it's very good. So if you go to the Abaqus documentation, these are some of the things that you may look into it, but the whole subroutine looks like this. Okay, so you just copy and paste this one, you just copy and paste this one. Okay, but you have in subroutine in VUMAT, so you can see that this is its subroutine as I mentioned. So this has the structure of subroutine. You have VUMAT, and you have there is a structure in it. There is here you declare variables, and these are different variables. And if you want to know what are these variables, for example, n block, ndir, whatever, all these variables, there is an explanation here. Variables. So these are the variables, input variables. You can see the list of it here in Abaqus documentation, but in our example we just need one or two of them. And the things that you should define is stress neo or state variables, these two. But we don't have state variables here, so we have only this one. You have to define the stress, but remember that the stress measure in VUMAT is co-rotational stress. So if I go back here, it is you have to define co-rotational stress. So whatever you do, you calculate based on your constitutive matter, you have to transform it to co-rotational stress. So this is a subroutine that I've prepared for for a neo-Hookean material. So these are basics. I just copied and pasted. Okay, so I copied and pasted them from the Abaqus. There is one catch here which may a little bit be hard for you to, I mean, it was hard for me to understand at the first time, but anyways I have to go through it. It's this do and continue. So this is like do and do, but this is another form of it. You don't have to learn it. It's quite complex. How this is the Fortran language. So in Fortran 77 initially they had to define each loop. For example, this is loop 100. So do 100, this is the name of the loop, and when you want to end that loop you should put it here. This is the Abaqus. In the explicit Abaqus, it gives you the whole structure element. So you have n block, so it gives you a matrix. For example, for deformation gradient, it gives you a matrix which has six columns. 6 columns, which excuse me, 9 columns, F1, 1, F2, 2 until F1, 3, but it has n block rows. So for each n block, which is here, you can see it here, it is the number of integration point in your model. So if you want to, I'll go back to it later on to say what I mean, but it is important. So you have to define it for each integration point. What you should do is, for neo-Hookean, the only thing that you need is, if I find it, deformation gradient neo, yeah, this one, it should be here, yeah, here, deformation gradient neo, deformation gradient, you need that one. because your model is elastic. So with that one you're done. There is another point here. As I mentioned, in Abaqus, when you want to use double, you should put D0 or I mean, you have, if you want to have double precision, you must put D0. So the people usually make mistake and don't put it. Instead, what they do is they define parameters. 0, they define it 0.D0. They define some common numbers here: 1, 2, 3, third, which is 1/3, and they define it once. Well, once they defined it, they don't have to use it again. So I'll go down one by one, so line by line, and explain everything. So this is your variables. You from here to here, you copy and paste it from Abaqus, okay, from the documentation. So these are the inputs. The other thing is, here I have defined some new variables, and because they were array, I have to define their dimensions as well. So these are the dimensions of the new variables, internal variables in my code, and this is the parameter. I sometimes use it. So here, if you look at it, mu, this is the material parameters. If you look at the neo-Hookean solid, you have two parameters, kappa and mu. So mu, I cannot start it with an m because I have included this subroutine, this file. So mu is an m. Any variable starting with an m, it's an integer. So I put an a here, and also the same goes for kappa. So I use a cap. So these are material parameters that you're using. Here I wanted to define identity matrix. Identity matrix, I defined it I, and it is 3 by 3, and so it's all of the elements are 0 except those which are on the main diagonal. So for 1, 2, 3, I should put 1, and 1 I have defined it here. It's 1.D0. So as I mentioned, you should go to the 1 to n block. So what it means that you have all the information at the same time. So for example, if you go to the deformation gradient, you have 9 elements. But for each integration point at the ith column, the column number I, you have to look into it and get your deformation gradient. So I haven't declared I because it starts with I, it's already integer. So deformation gradient, it is given by Abaqus. It is given by Abaqus, so you don't have to. So this is a given data. I'm just restructuring it into deformation gradient. So f is the deformation gradient, but I have defined f here. It's 3 by 3 matrix. I have defined it here, the dimension of it, and the next one is the stretch tensor, which is u. I have defined it xu here. I don't know why, but I defined it xu. Stretch nu, it is given by the Abaqus. So I'm just restructuring it. In the I column, I go to the one, and if you want to know which element corresponds to which tensorial element, because this is vectorial form, you can go and look at the here in the documentation. For example, component 6 of the stress is sigma 3,1, and you can see that here, because you have symmetry, it doesn't give all of it. So sigma 3,1 is equals to sigma 1,3. So there is a symmetry here. Exactly the same thing happens, but not for the deformation gradient. It's not symmetric, so you have 9 elements. The same goes for the stretch tensor. So here I define the symmetries. So XU again is a matrix, a 3 by 3 matrix. I forgot one thing. So if you want to calculate the deformation, if you want to call or use any subroutine, you should use this. You should call, this is the typical format of it. You should use call and then the name of the subroutine. Here I want to calculate the determinant of the matrix XU, the stretch matrix. I call the determinant, I calculate the determinant, which is XJU, and then I calculate the inverse of it. Why I want to calculate the inverse of it, of the stretch tensor? Because I want to calculate the rotation matrix. F equals R, so R equals F multiplied by U minus 1. So if I calculate the inverse of stretch matrix and I multiply F by the inverse stretch matrix, I can calculate, I can get the R, the rotation matrix. So that is why I calculated here the determinant. Then I have defined the inversion inversion operation, and I calculated the inverted matrix U minus 1, which is U, which is inversion of the U. And then this is a function that you can use, mat multiplication. So if you have two matrices, you can multiply two matrices by this function. This is a predefined function in Fortran. It is mat mul, which stands for matrix multiplication. So I define the rotation matrix. Again, I have defined it at the beginning. It's a 3 by 3 matrix. So rotation, it's F multiplied by the inversion of U. So I have calculated the rotation matrix. So here the rest is pretty clear. So what I have done until here is that I have restructured F. I have calculated, if you look at it, I have restructured. It's pretty simple. It may seem complex. I have calculated F. I've calculated, I have restructured the stretch tensor. I have calculated the rotation matrix based on this formula. But because I wanted to use this formula, I had to calculate the inversion of U. Now I want to calculate the stress in a neo-Hookean matrix. So I need I. I have defined I at the beginning. So I is this one. So I have defined the identity matrix, okay? Then I have to define B. The B. What is B? B here. B is F transpose. F transpose. So the transpose is another predefined function that you can use. These two, in calculating inversion and determinant, I wrote them. These are not in the Fortran, but mat mul and transpose you have them. So I've defined B. Again, B, you have to define it as a 3 by 3 matrix, okay? P, B, rot, X, U, F, you have to define it. Then I wanted to calculate the determinant of the F, which is J. So I need J. Kappa, I have it. Kappa and mu, they are constant. So I have to define J, B, and I have to define B star. B star. What is B star? B star is this formula. So it's pretty simple if you look at it. B star, which is defined BST, it is this, and I want to calculate this, the first invariant or trace of B star. If you look at it, I've used AI1B. I couldn't use I1B because if I use I, it takes it as an integer, so I added an A. at the beginning. So it's just calculating the trace. Then the deviatoric part of it, deviatoric part of the B star, which is this formula. So it's again pretty simple. I just implemented in this formula here, and now you have everything. You have everything. You have this. You can put it into Fortran. So, but when you calculate it, it fits in one line, but I made it 2 lines just to use this notation here. I just wanted to show that you can use that. So a cap multiplied by this, and again, and notice that I have used 1 instead of, it is equivalent to using this, but sometimes when you use this you forget to put D0 and it messes up your calculation. The next is you want the sigma. You want the sigma because this formula gives J sigma. So if you want to calculate sigma, you should divide it by AJ. So until now you have calculated the co-shear stress. Now you have to rotate it to make it co-rotational. You have to do this. What you can do here is you can use this formula, and I just put it in a Fortran. It's 2 multiplication and 1 transposition, and then what is the new stress? The new stress is co-rotated sigma, and I just defined it. So it's pretty simple. And if you want to run it, there are some points. It's quite easy. I will send you the files, you can figure it out. But there is one point. When you want to use a subroutine, you should use this. Okay, you should go here. You have a user subroutine. You should select your subroutine here, and it should have .4. It depends on the system. Sometimes the file type it's F19. Sometimes it's .f. For my system it's .4 or Fortran. And the next thing is the precision. I have used double here, but again you can use single. It doesn't change anything. But for this model it's not important. But in many cases it's very important if you use single precision or other things. So here I have used double because it takes more time, but it is more accurate. So I submit it, and I wait until the completion. I've used a very coarse mesh because Abaqus explicit takes a lot of time, but it's okay. And I like very much Abaqus explicit because it's much simpler than VUMAT, and it's much more, it has less headaches. So if you look at the results, that's it. And you can compare it with the VUMAT, with the neo-Hookean that you have in Abaqus. It should be the same, although I've written it by myself like today, and I'm not sure how I can do it. Oh, another point is if you want to print something so it's pretty simple. If you use for example, you want to print this one, Alec. You want to print this. When you use this, when you use this one, for example, you want to debug your subroutine. If you use this one, in the log file, I haven't run it, so you can see there is nothing in my log file. But let's put it simple, because this is a good thing, but it also increases your computation time, and because when Fortran is going to write it down in the log file, it takes a lot of time. This is one of the things that Fortran is really bad in it. It's writing a text file. It's terrible. So yeah, you can see that it is written. The the first components of the stress. You can see it. So if you want to write down something, you use print star something, whatever you want to write it down, and you can see it in the job. You can see it in the log file. So I think it's done, and if you have any questions, just send me a text or email. We'll figure it out. Thank you.